All right, so Henri LeChatelier. So he came up with this principle after studying factors that affect equilibrium in the late 1800s. So it's kind of old, although, there was some chemistry going on in the 1650 and beyond. So this is, I don't know. I guess I was actually surprised that it was that long ago, right, that someone was talking about this, right? But remember, Wege and the other guy were talking about the law of mass action right around this same time, okay? So Le Chatelier is kind of in that same mindset. So he came up with this principle. And it says, when a system, and what for us the system is the chemical reaction. When a system at equilibrium is disturbed by a stress, in quotes there, stress. Well, what kind of stress? Well, we'll see. There's 5 possible stresses. The system, the chemical reaction, will respond to eliminate or to try to reduce the stress. And then the equilibrium, the reversible reaction, will reach a new equilibrium state. So when you do something to the chemical reaction to stress it out, man, right? The reaction wants to reach equilibrium again. You disturb the equilibrium and the reaction is going to want to respond. And it's going to want to set up a new equilibrium. So what are some of the possible stresses? Well, we're going to go through each one of these 5. So if you don't want to hurt, well, you have your notes written out there, but if you didn't have to furiously write this down. But it's going to be concentration, pressure, temperature, dilution, which applies to aqueous solutions only, just like pressure applies to gases in an equilibrium reaction, and then catalyst, introducing a catalyst. What's that going to do to stress out the equilibrium? Okay, so these are the possible ways you can stress a reversible reaction. Okay, and again, we're going to take each one of these and go through the thought process is, what if you change the concentration of reactants on a reversible reaction? How will it respond? What if you change the pressure? How would it respond? Okay? All right, so let's say that we change the concentration on a system of equilibrium. Okay, it's going to be disturbed, and there's 4 different things you can do. You can add some more reactant. You can take away reactant out of the mixture, right? You can add something to the product side, or you can take away something from the product side, okay? And then what's going to happen if we add something, if we add reactant, well, what's the system going to want to do? Well, it's going to want to reduce the amount of reactant you just added, see? What if you take away reactant? Well, the system is going to want to restore the reactant that you pulled out. You see, it's trying to reach a new balance. So it's always going to respond, as we're going to see, in a way to undo what you just did. If you take out some of the product, you harvest some of the product, well, the reaction is going to try to hurry up and make more product because you just took away the product, right? It was in balance, okay? So it's kind of like think about it when we did the buckets of water experiment. So when we did the buckets of water experiment, some of our buckets of water, depending on which size beaker we had on forward or reverse reaction, some of ours ended up like this, where at equilibrium, the reactant to product ratio, I don't know, this looks like about a 3-to-2 ratio, right? And it was there, right? And those reactant and product concentrations stayed constant. But now, and the forward rate and reverse rate were equal. But now, imagine what would have happened, and we didn't do this, but what if I would have gone along and you're at equilibrium, and then you add a bunch more reactant, like you see here in green? Well, what's going to happen with the next scoop? Isn't the forward scoop now going to be larger? The forward rate going to be larger than the reverse rate? At least on the first couple of scoops, yeah? And think of what's going to happen. So as you do this, right, it's gonna kind of, what I say, it kind of kickstarts the forward reaction. So they were in balance, and now kind of like the way I guess you would show that, I guess I should have written it this way. Kind of what happens then is like this rate is going to be larger than this rate, at least initially, right? But what's going to happen over time? Well, the reactant concentration is going to go down, right? And the product concentration is going to go up. and you're going to reach a new state of balance, right? You'll reach a new state of balance, and then the rates are going to become equal again. So you're going to restore the equilibrium. But how did the reaction respond? You added reactant, and it responded to try to shift reactant away, right? Get rid of the reactant you dumped in, okay? Then it's going to reach a new equilibrium point, and I probably didn't draw that very well, but it would be a 3-to-2 proportion. In other words, it's going to reach the same exact KEQ, right? As long as you're at the same temperature, KEQ is a constant. Does that make any sense, I hope? Yeah? Okay. So we're going to go through, now we're going to look at each one of the 4 possible stresses, like increasing reactant, decreasing reactant, increasing product, decreasing product, and work through this like sort of 4-step process in deciding which way and how is the reaction going to respond. Okay, so let's say that I increase the reactant. Well, what LeChatelier's says is that the system is going to want to decrease the amount of reactant, right? So if I increase the amount of reactant, the system is going to want to do the opposite, undo what I just did. Well, in a chemical reaction, what can the chemical reaction do to decrease the amount of product? What's going to happen is the forward rate is going to increase, right? We kind of saw that with kind of my buckets of water example, right, just before, right? The forward rate will increase with respect to the reverse rate. And so you're going to have movement from the reactant side to product side. So initially, now eventually the rates are going to become equal again. But the first response, how are you going to do? You're going to shift, the reaction is going to shift, we say, toward the product side. This is what you would say, it shifts toward product. Sometimes you say it would shift to the right, okay? But I like saying toward product or reactant better than right or left, okay? I think it's just a better way to say it. So in other words, you're going to shift, we say the reaction shifts toward the product side. Now, it's not going to shift indefinitely because it's going to reach a new equilibrium. But like a lot of times with LeChatelier, what you want to know is which way, how is the reaction going to respond right after you disturb it? You know it's going to reach a new equilibrium point, but how does it respond initially, okay? What if I decrease the amount of reactant? Well, if I take away reactant, the system is going to want to increase the amount of reactant, right? And that it does that by increasing the reverse rate. The reverse rate will temporarily increase, right? To restore the reactant that was removed. And so we say that the reaction shifts toward reactant. Make sense? What if I increase the amount of product? I dump in a bunch of product. What's the system going to want to do? Reduce the amount of product you just added. Well, what's that going to do? Which way is it going to shift? Somebody. To decrease product, you have to shift toward reactant, right? And it's going to do that again by temporarily increasing the reverse rate. And then again, the rates are going to become equal. And then the concentrations will remain unchanged. But the first response, move toward the kickstart the reverse reaction with respect to the forward reaction, and that'll cause product to decrease, and you'll shift to the reactant side, okay? What if I take away product? Now, this is a classic way to make more product in a reversible reaction. Think about this. I harvest some product. So I don't have any product in there. Well, what's the reaction want to do? It wants to restore the product you just removed, right? And so it's going to kickstart the reaction to the right-hand side, yes? And so, right? And then you're going to make more product. So we say it shifts toward product. Okay? And then it's going to reach a new equilibrium point, but it'll have the same proportion. Okay? So let me scroll down here, and I sort of have a little graphical example. All right? I may not have drawn it perfectly, but I'm going to try to explain what it is. Okay, do that. Okay, so it reaches a new equilibrium value. So that, okay, so here we go along, look in red, or whatever that color is, right? Reddish brown. And we have the reaction reaches equilibrium. It's nice, it's happy, it's at equilibrium. And I come along and I dump in a bunch of reactant, right? Well, what's going to happen is, you see kind of how we add more reactant, and so it's going to hurry up and start trying to get rid of that reactant, right? And in the green line, you can see that it's trying to get rid of reactant that I added, right? It's getting rid of reactant, but in that same case, then it's making more product, right? But when it reaches the new equilibrium, the proportion will be the same. The product over reactant proportion will be the same. I may not have drawn it perfectly, but whatever that is, like maybe I don't know, again, a 3:2. Maybe I didn't draw a 3:2 in green, but it would reach that same proportion, product to reactant, because the KEQ value does not change here. All right? All right, so changing this up, let's see what would happen if I would remove product. Okay? Well, what's going to happen is the system is going to want to restore that product, correct? And so what's going to happen is, right, it's going to kickstart the forward reaction, yes? And so the reactant concentration is going to go down, right? Because you're going to shift to make more product. And then the product concentration, which had dropped to here because you removed product, it's going to come back up. And look at that. Now you have more product. So you harvested product, right? And now you caused the reaction to make more product. What could you do again? You could remove this product that it just made, right? You could remove that. And what's it going to do? It's going to kickstart the forward reaction to make some product, and the reactant's going to go down, right? And then eventually, look what you're doing. You're dropping the reactant amount down and down and down. Got it? Why? And you're making more and more and more product. So if you have a chemical reaction where where KEQ is less than 1, like this one is drawn, right? You have more reactant than product at equilibrium, at the initial equilibrium. You can drive this reaction more and more toward product by harvesting the product out and making the best of a bad situation where you have not a very, this does not favor products, right? This initial reaction. But you could keep driving it toward the product side by removing the product that you made if you can harvest that without, removing the reactant. And if you do that, you're going to kickstart the equilibrium and keep making more and more product. Okay? All right, well now, why does this happen? Why does the change in concentration affect the equilibrium in this way? Well, it's all going to boil down to Q versus K. Remember, with Q, if Q is greater than K, it means you have, quote, too much product for the amount of reactant at equilibrium. And if you have too much product, you'll shift toward the reactant side. If Q, your reaction quotient, is less than K, right, then the system is going to want to go toward the product, because if Q is less than K, it means you don't have as much product as you should have, quote, at equilibrium, all right? So let's kind of look at this, and what we're going to do is we're going to have this system here, the making of ammonia, the process to make ammonia, and I looked this up at 700 K. The KEQ for this is 0.29, okay? And that would result if you had, these molarities at equilibrium. Now these are the equilibrium concentrations, okay? So not the initial concentrations, these are the equilibrium concentrations. And so if I plug these numbers into my KEQ expression, I should get 0.029. Okay, so plugging in these values here in green, these are the equilibrium values. So I'm calculating KEQ for this reaction. I'm telling you it's in equilibrium. If you do the math, you get 0.29, right? That's what the KEQ is. Perfect, okay. But now, what if we come along and we disturb this equilibrium by adding some more nitrogen gas, okay? We're gonna disturb this, and we're going to add nitrogen gas until this concentration now is 1.50 molar. Got it? And then so the system is going to respond, right? And now you could probably tell, right? You're not going to have 0.29 for your value anymore, right? Because when you plug, okay, I'm not at equilibrium now. So when I calculate the next value I'm going to do, that's actually the reaction quotient, Q. I disturb the equilibrium by adding in more nitrogen. So the reaction quotient for this guy is going to be, right, it's going to be, we're going to say, it's going to be so it's still going to be 0.198 initially, like when you first disturb the equilibrium by adding the extra nitrogen. But then the nitrogen here is going to be 1.50, and that's still going to be times the 3.00 molar hydrogen cubed. Okay? And if you do this math, when you find it, you know it's going to be a smaller number, right? Because this is what we did before. We're dividing this same 0.198 squared over 3 cubed. We're dividing it by 0.5. Here we're dividing by 1.5. If you calculate this, the reaction quotient is 0.97. That makes sense, right? Because you've increased the concentration here, and so Q, right, is less than K. And so which way is the reaction going to shift? Well, when Q is less than K, what that's saying is, remember, product over reactant is smaller than it should be at equilibrium. And if product is smaller than it should be at equilibrium, the reaction is going to try to make more product, right? Because Q wants to become K, and the only way it can do that is to make more product and get rid of more reactant at the same time. See? So why does the reaction shift like this? It all mathematically boils down to Q versus K. All right? So you have your, you might be asked with LeChatelier's principle for just which way is the reaction going to shift? Which way is it going to kickstart? But you might also be asked to prove or justify it using a mathematical situation, and you'd be given the numbers here and you could prove it. Like, why does it shift that way? Because in this case, when you dump in reactant, Q will always be less than K, right? But what if you dump in more product? If you dump in more product, Q is going to be greater than K. And it's going to shift the other way, see? So this is the mathematical justification. Okay, so I have this system in equilibrium. I come along and I pull out some of CO2. Which way is the reaction going to shift? So I remove CO2. The system is going to want to respond to restore the CO2. Yes? That's my second thought. So what I did, I removed the CO2. The system wants to respond to restore the CO2. Well, how is it going to do that? Which way is it going to shift? To the product side. Right? And it'll do that by temporarily increasing the forward rate. Yes? Compared to the reverse rate. Okay, what if I come along and I take out CO2? The system is going to CO. The system is going to want to restore the CO. Which way is it going to shift? To the reactant side. Okay, now here's a kind of a trick question, and I'm going to point out the fact that this is a solid. Okay, do solids affect equilibrium positions? No. So I could add more Fe2O3, I could take away Fe2O3, and this would be a no change. Remember, it would be like, think of it like I have a solubility equilibrium, right? And I have some calcium fluoride at the bottom of the beaker. I could add all the calcium fluoride I want, and no more is going to dissolve, right? That pure solid is not going to affect the equilibrium position. So this will be a no change. You would say no change or no shift. No change to the equilibrium position. So you got to be careful when you're asked a LeChatelier's principle question. If it's a pure liquid or a pure solid and you change the amount, it will not shift the process. Okay? All right. Woo! Okay, so pressure changes. And pressure is changed by either increasing the volume of the container or decreasing the volume of the container. First of all, pressure changes only affect equilibrium with gases involved. If I had a solid calcium fluoride in equilibrium with its aqueous ions, changing the pressure isn't going to do anything at all because they're not gases, right? Remember, pressure only affects gases. Okay, so thinking about this, if I decrease the volume, on a reaction, mixture of gases. Decrease the volume, so it was here in it was red, and I push the top down to where it's black, right, this line here, okay? I'm going to decrease the volume, the pressure increases. And so what LeChatelier's principle says is, if you increase the pressure, the system wants to undo that. It wants to decrease the pressure. Well, the only way a system can reduce pressure with gases in it is to lower the number of moles of gas. Because what causes gas pressure? The more gas particles hitting the sides of the container. If you have fewer gas particles hitting the sides of the container, the pressure will drop. And so what this causes, it causes the reaction. If I increase the pressure, the system wants to decrease the pressure, and it can only do that by reducing the number of moles of gas present. All right? And so thinking about that, one, what if I increase the pressure? What if I started out with the piston in this container where the black line is, and I raise it up to the red line? Well, you're going to decrease the pressure, and the system will want to increase the pressure. To increase the pressure, a chemical reaction can only make more moles of gas. And so it'll shift to the side with more moles of gas. So let's go through the two scenarios here. Okay? I have a system, two NO2s are in equilibrium with its dimer or something like that. It's like N2O4. Okay? One of these is extremely toxic. I forget which one it is, the NO2 or the N2O4. It's a really toxic orangish brown gas, and the other one is colorless. All right? I think it's still not great to breathe in, but the other stuff is deadly. Okay? Anyway, so I have this equilibrium, and I increase the pressure. If I increase the pressure on this system, now remember, you're increasing the pressure on both things. You're increasing the pressure on both things. A lot of people think, oh, I'm increasing the pressure, and I'm only increasing the reactant side. No, all of these are present at the same time, right? The NO2 and the N2O4, are you with me? They're all present at the same time. When I increase the pressure, it's on the whole system. The system has to respond to decrease the pressure. Well, what it's going to do, in this case, it will kickstart this reaction in the forward direction because the product side has less moles. Okay? So how does it decrease pressure? It makes less moles of gas. And in this case, and it's not always right or left or product reactant, it's whatever direction. It's going to shift in the direction with the fewer moles. So in this case, it will shift to make more product. Does that make sense? Because the product side has less moles of gas. And if I have more N2O4 and less NO2, the pressure in this container will go down. Got it? Because they have fewer particles hitting the walls. Yes? Make sense? Yes? 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 Okay. What if I decrease the pressure by increasing the volume? Well, the system's going to want to restore that pressure. And it can only restore pressure if it makes more moles of gas. So it's going to respond by wanting to make more moles of gas. And to do that, in this particular case, it will shift toward the reactant side. Okay? And it's going to, again, reach a new equilibrium, but still have the same equilibrium constant value. It'll reach that same proportion. So initially, it's going to kickstart the reaction, in this case, to the left, right? To the reactant side, if I decrease the pressure on this particular equilibrium system, but then it'll reach a new equilibrium, okay? And the rates will become equal again. It'll respond as much as it can to increase the moles of gas as much as it can, or decrease the moles as much as it can, and then it will reach a new equilibrium, all right? And again, on that handout I gave you, there's an example. Again, it's not, they don't plug in numbers, but they show you how this would work, Q versus KYs, using pressures. Okay? Okay, let's go through an example where I just ask you kind of what would happen, all right? So now I have this system here. 2NOCl is in equilibrium with 2 NOs and a Cl2. What if I come along and I increase the pressure on this system, not on the reactant side, not on the product side, on all of it? Because that's a misconception, right? When you increase the pressure, you're only increasing the reactant side. They're all in the vessel together. They're all in this together, right? Like High School Musical? No? You guys are too young to know High School Musical, right? Anyway. And they're the Wildcats, right? In the movie, in High School Musical. Anyway, so what would happen? Which way is it going to shift? Toward the reactant side, because the reactant side has 2 moles of gas and the product side has 3 moles of gas. So if I increase the pressure on the system, it will respond to reduce the moles of gas by shifting to the reactant side and then reach a new equilibrium. Okay, so when I look at these and it's a gas, I just write about like, oh, this has 2 moles of gas, this side has 3 moles of gas, and then you decide. Okay, how about this next one? How many moles of gas are on the reactant side? 2. How about on the product side? 2. So what if I increase the pressure on this baby? No change, because no matter what this reaction does, it's not going to be able to change the pressure. So it's just got to suck it up and be pressurized, right? The system can't respond. It wants to respond, but no matter which way it would shift, it's going to stay the same. So this actually does not change. This reaction cannot shift to try to reduce the pressure. The pressure would just be increased on both sides. Yes?
Is there a way to like change that so like it can react afterward? Or?
No, I don't think so. As long as you have that 2 to 2 mole proportion, there's no way to change that. Now, what you could do is remove some of the hydrogen and iodine gas. Okay, no, but that's more of a concentration thing then, right? By removing product, you could then kickstart it to make more product. Now, yes, that would decrease the pressure temporarily if you take those gases out of there, but what they would say is you would remove that product at constant pressure. You know what I mean? Like, so the container would adjust, okay? So when we look at these LeChatelier's, yes, that's a good point. We kind of look at them in isolation. Like, here, we could pressurize this, but the concentration stay the same or something like that. You know what I mean? It would be the same, okay? Okay, again, temperature. I can change the temperature, and what's gonna be important here when you change temperature is the thermicity of the reaction. Is it an exothermic reaction in the forward direction or an endothermic reaction in the forward direction? And tomorrow I'll do a quick demo that illustrates the effect of temperature on the equilibrium position. So we'll actually be able to see this effect tomorrow. So I have this equilibrium system, and it's exothermic in the forward reaction. So let's say, what's one of the things I can do to temperature? Well, I can raise the temperature on this system, yeah? I can raise it by adding heat, all right? Well, if I raise the temperature by adding heat, the system is going to want to decrease the temperature. It's going to decrease the temperature by consuming heat, yeah? Well, which direction would this have to go to consume heat? Toward the right or toward the left? Toward the left, right? Left, right, got left, correct. So it's going to consume heat. And so the reaction here wants to consume heat because you added it. So in this case, it will shift in the endothermic direction. And this, in specific, for this reaction, the endothermic reaction will be toward the reactant side. Okay, what if I decrease the temperature by removing heat? Well, the system is going to want to increase the temperature by producing heat, right? How can a chemical reaction raise its temperature? By producing heat. Well, this reaction, as written in the forward direction, produces heat. So it's going to shift to the product side, yes? So it's going to shift to produce heat. You shift in the exothermic direction, which in this case is to the product side. Make sense? So again, see what I'm doing here? Okay, here's what you did. Here's how the system wants to respond. Then you ask yourself, how can the system do that? And in that is your answer. To consume heat, you're going to go in the endothermic direction, yeah? And whatever that direction is for the reaction, for written. If I want to produce heat, right, I decrease the temperature, so the system wants to increase the temperature. How can it do that? By making heat. How does this reaction make heat? By going in the exothermic direction. Got it? So if every one of these you kind of think, what did I do? What's the system want to do? The exact opposite, like your pesky little brother, right, that always wants to do the opposite of what you do, right? All right, and then, how we will respond. Okay, let's look at another example that is endothermic as written. Okay, here's that same equilibrium that I had on the previous page, but I put in the heat term. So if I increase the temperature, the system's going to want to decrease the temperature. So it's going to want to consume heat. So which direction is it going to go in? It's going to go toward the product, right? It's going to reduce the temperature by consuming heat, so it's going to shift to the product side because that will consume heat. Increasing temperature, decreasing temperature, the system wants to increase the temperature. It's going to produce heat, again, make heat. And in this case, it would then go toward the product side. I'm sorry, reactant side. I drew the arrow in the reactant side, but I said the wrong thing. Reactant. Okay, how about this example? So H2 plus I2 makes 2HI. It's an endothermic reaction as written. If I decrease the temperature, which way will this guy want to shift? It's going to want to do what? If I reduce the temperature, the system is going to want to do what? Increase the temperature by producing heat. Which direction would this reaction produce heat?
Reactant.
Toward the reactant side, right? So if I decrease the temperature on this reaction system, it will shift to the left or shift to the reactant side. Make sense now? Okay. And again, I think, you guys just have to, you're going to have to just work through the examples on the homework to kind of nail this down. Okay, we got a motor here. So what is the effect? So KEQ, okay, if you have a reaction that's endothermic in the forward direction, and you increase the temperature, you're giving the reaction what it needs. The value of KEQ will go up. So if I have an endothermic forward reaction and I raise the temperature, you are giving it what it wants. You'll get a new KEQ. It's going to reach a new equilibrium, but the KEQ value will be higher. If I have an exothermic reaction, right, a reaction with an exothermic forward direction, okay, and I raise the temperature, it's actually KEQ will decrease its value. So here's just a quick example, and you have the numbers here, and they're on your notes right there. Let's look at this. So this reaction is exothermic in the forward direction. Look what happens to the KEQ for this reaction. And I looked these numbers up online. These are available online. It's a very famous reaction. At 400 K, the KEQ value is actually larger, right? Because this is exothermic, as I raise the temperature, it will reach a new equilibrium. Temperature is the only thing that affects the value of KEQ. All the others, it'll reach a new equilibrium, but keep the same KEQ value, all right? So here, this reaction would be better done at a lower temperature, right? Because you get a lot more product. Here, at 700 K, the reactant side is favored. At 400 K, the product side is favored. You got it? And so it all boils down to how it affects the value for the K for the forward and reverse rates of these reactions. Okay? And that's all you need to know about that. Okay, let's real quick look at dilution. If I have only aqueous things, right? If I have a solution with aqueous ions, this is very much like pressure. Stay with me here in the last minute. Okay, if I have a system, this is a very famous system. The stuff on the right is blood red. The stuff on the left-hand side is colorless. When they combine to make this complex ion, it turns blood red. It's kind of cool, right? So let's say I have this reaction and it's at equilibrium. Okay, these ions are in equilibrium with one another, and I add a bunch more water. Well, diluting is like reducing pressure. Right? In other words, if I add a bunch of more water in here, I dilute the concentration, don't I? Well, the system wants to restore the concentration of ions. How can this reaction restore the concentration of ions? Shift to the side with the more ions. In this case, to the reactant side. In other words, I have 2 moles of ions on the left, I have 1 mole of ion on the right. If I dump in some water, the system will want to restore the concentration of ions. So it's very much like pressures and gases. And then finally, in the last minute here, catalysts. Turns out that catalysts don't affect where the equilibrium position. All it will do is you reach equilibrium faster, but a catalyst does not change. I can add a catalyst, and what happens is the catalyst equally increases the forward and reverse equally, right? Because a catalyst doesn't just catalyze the forward, it catalyzes the reverse reaction also, and so it just reaches equilibrium faster. But it won't, catalyst will not change the equilibrium position, okay? In a sense, forward and reverse are kick-started equally. Got it? Okay.
All good?
Yes, we're good. Thank you.
Read the homework.
Oh.